Here we're looking at the radioactive decay. This problem is taken from OpenStax 10.3, problem number 37. And the problem is asking us if we have the initial number of the radioactive nuclei, which is 2.4 times 10 to the negative 2 moles, and the half-life of this material would be 6 hours. Then how many radioactive nuclei do we still have after the decay for 6 hours, 12 hours, and 36 hours? So here I have two methods in approaching this problem. So after I define the problem, I start with this formula, which is derived from the radioactive decay law. And it says that the decay constant is just a constant multiple of the inverse of the half-life. And so we calculate by plugging the half-life with the half-life we have. So we have this decay constant in terms of our inverse. The radioactive decay law is this equation right here, and it relates the number of neutrons we still have after the decaying by an initial number. So this negative means that for whatever time we spend as it's increasing, then we should have less and less neutrons. So at 6 hours, we just plug in T equals to 6, and we have 0.012 mole. At 12 hours, we have another value, and 36 hours, we have another value. And we conclude by saying that for these number of moles, so for these number of times, 6 hours, 12 hours, and 36 hours, we have this and this and this mole. And you could see it is decreasing, and it makes sense because it is decaying, right? So that is method 1. But for method 2, we approach with we have another approach. So we identify from the problem that the half-life is 6 hours. And the problem is asking us how many radioactive sample we still have after 6 hours, 12 hours, 36 hours. So note that 6 hours, 12, and 36 is just 1 half-life, 2 half-life, and 6 half-life. So we have here, this is 1 half-life, 2 half-life, and 6 half-life. So what half-life mean is if we have initially we have 100 neutrons, then after 1 half-life we will have 50 neutrons. It decreases by 50%. So we could just divide the initial number by 2. So we have 0.012 mole. And similarly, we just divide this thing by 2 again. Sorry, not this. We just divide the 0.012 by 2 again to get this thing. And for 36 hours, we do the same thing here. So we have the same answer here. So for a little bit extension here, I'm going to talk about activity. The activity is a measure of the magnitude of the decay rate. So we're talking about dN over dt. And if we relate everything, we have A equals to A naught, and this should be e to the negative lambda t. So A naught would be the initial activity. So before everything start, what is the activity of the decay constant? Sorry, what is the rate of the material decaying? And basically, this the A naught would equals to the decay constant times the initial number of the neutrons. So we have to calculate the initial number of neutrons. We are saying that because everything is in terms of moles, and if we're doing activity, it's better that we convert it to atoms. So we just multiply by the is it called the Avogadro's constant, something like that. But this relates to how many moles to how many actual atoms there is in the material. So if we convert that, then we have the initial activity with this constant. And and we're saying that A is also equals to A naught e to the negative lambda t as to calculate the activity at certain time. So we could see that as time is longer or the value of t is bigger, then A same thing as n should be smaller and smaller because the rate of decaying would be smaller and smaller. And that concludes radioactive decay.